Project Planning and Control, PPNC. Planning and Baseline Architecture. Course 3, Module 2. This will be an introduction to schedule assessment. Module 2 covers schedule health assessment, from the financial stakes of schedule growth through DCMA metrics, critical path analysis, execution indices, and historical mission data studies. The foundational principle of this module is that schedule drives cost, and that for every 1% of schedule growth, expect equal or greater cost growth in a cost-plus environment. After this module, students can assess schedule credibility independently, identify the most common schedule failures, quantify execution performance with BEI/HMI/CEI, and advise on recovery options. Every cost overrun on a major government program involves a schedule problem somewhere upstream. Understanding schedule is not optional for a cost analyst. Schedule credibility is one of the strongest indicators of whether a program will ultimately succeed. Research has consistently shown that schedule growth is often accompanied by cost growth, making schedule assessment a critical responsibility for PPNC professionals. In this module, we'll learn how to determine whether a schedule is realistic, executable, and capable of supporting program objectives. We'll examine industry-standard assessment techniques, including DCMA health checks, GAO best practices, critical path analysis, resource loading assessments, and key schedule performance metrics. By the end of the module, you'll be able to identify weaknesses, recognize emerging risks, and assess whether a schedule is truly positioned to support successful program execution. By the end of this module, you'll be equipped to evaluate schedule health and determine whether a program schedule is realistic, executable, and capable of supporting mission objectives. You'll learn how to apply industry-standard assessment techniques, interpret key schedule performance metrics, analyze critical path and resource loading risks, and identify early warning signs that may affect program success. You'll also develop the ability to assess schedule credibility, recommend corrective actions, and communicate findings in ways that support informed leadership decisions. These skills are essential for understanding how schedule performance influences overall program outcomes. This section title slide opens the schedule assessment module, a signal to students that the analysis tools being taught here are specifically focused on the schedule dimension of integrated program health. Schedule assessment is distinct from scheduling. Scheduling is building and maintaining the IMS. Schedule assessment is the independent evaluation of whether the IMS is credible and whether execution is on track. The distinction between the tool user and the assessor is important. This module is about the assessor role, not the scheduler role. Most programs have a dedicated scheduler. Not all programs have someone independently assessing whether the schedule that scheduler produces is believable. That is the PPNC analyst's job. The financial stakes of schedule, 250 workers at a $200,000 loaded rate, means $137,000 burned every day. An average slip of 25.8 months, based on historical data, costs $106 million. These numbers make schedule assessment concrete. Every day of schedule slip on a program of this size costs $137,000. Every month costs approximately $4 million. The average slip of 25.8 months comes from the 114 mission NASA study covered later in this module. It is not a worst-case number. It is the average across all mission types. The next time someone suggests that a schedule assessment is less important than a cost analysis, show them these numbers. Schedule is the largest single driver of cost growth on most government programs. Understanding the scheduling process, tools, and techniques is necessary, but not sufficient. We also need to understand the engineering and manufacturing system being scheduled. A schedule built by someone who has never visited the fabrication floor, talked to the engineers, or observed an integration activity will reflect scheduling tool proficiency, but not manufacturing reality. The scheduling challenge is not a technical one, it is a knowledge one. The tools are well understood. The work being scheduled is not always well understood by the person scheduling it. Schedule credibility assessment begins with asking whether the person who built the schedule understands the work it represents. Schedulers often know the tools but not the work. Mastery of Primavera and MS Project is necessary but not sufficient. Schedules may be mechanically correct but not realistic or risk-informed. The DCMA health check can pass perfectly on a schedule that has completely wrong durations because health checks test structure, not realism. The solution is to build domain knowledge alongside tool knowledge, not to abandon the tools, but to validate what the tools produce against ground truth. When reviewing a schedule, the first question should not be, does it pass the health check? It should be, does it reflect how the work actually gets done? Building technical understanding, study engineering drawings, review work packages with engineers, visit fabrication shops to learn cycle times and constraints, observe integration, and test. Visiting the fabrication floor is something most schedulers and analysts never do. It is also the fastest way to develop the ground truth that makes schedule assessment credible. Schedules that reflect real technical logic have fundamentally different characteristics from schedules built on assumptions. The durations are more variable, the dependencies are more specific, and the risk events are more visible. One afternoon in the fabrication shop is worth more for schedule understanding than a week of reviewing Primavera reports. Engaging with the project team, talk to engineers and production leads, meet supply chain and procurement, discuss with risk managers, joint status, and tag-up meetings. Early awareness of emerging issues is the primary benefit of this engagement. The analyst who is in the tag-up meetings will know about problems before they appear in the schedule. Supply chain lead times and vendor risks are frequently underrepresented in schedules because schedulers do not have direct procurement relationships. Closing this gap requires deliberate engagement. The analyst who is present in the daily execution environment will never be surprised by a schedule variance. The one who only reviews the monthly Primavera report will be. Integrating risk and realism. Incorporate risk assessments, validate health metrics against ground truth, recognize resource availability in network logic, capture lessons from prior builds. A schedule risk assessment that was not informed by ground truth knowledge of the fabrication floor and supplier chain will be less accurate than one that was, regardless of how sophisticated the Monte Carlo model is. Lessons learned from prior builds are one of the most underutilized scheduling resources. Historical cycle times from similar hardware development programs are available and routinely ignored. The transformation from contractual artifact to predictive decision tool requires connecting the schedule to the risk register, the resource plan, and the lessons from similar programs. The professional scheduler mindset, from tool operator to project integrator. Balance technical insight with scheduling discipline. The schedule is a living model of the work, not a reporting artifact. Value is measured by how well the schedule empowers decision makers, not by how well it satisfies the contractual data delivery requirements. The living model concept means the schedule should be updated every time the work changes, not just at monthly reporting periods, not just when a milestone slips. A schedule that accurately reflects current project reality is rare and valuable. Most program managers would say they have never seen one on a troubled program. Launch windows and the cost of buying schedule. Most planetary missions have fixed launch windows. Missing them means multi-year delays, and purchasing schedule through overtime loses efficiency. The productivity loss chart shows that extended overtime degrades efficiency steadily. 2 shifts and significant overtime are less efficient per hour, not more. If a schedule must be maintained, it must be purchased. But the purchase comes at a cost efficiency premium. The same work costs more when done under schedule pressure. When a schedule recovery plan involves overtime or additional shifts, the cost estimate for that recovery should include a productivity loss factor. The 40 spacecraft study. For every 10% of schedule growth, there is approximately 12% cost growth. The rule of thumb: every percentage of schedule growth leads to equal or greater cost growth. This is empirical data from 40 real programs. It is not a theory about how cost and schedule relate. It is a measured relationship from actual mission history. Variations can be significant. Some programs experience less cost growth per unit of schedule slip, others experience more. But the central tendency is clear. When a program manager says the schedule will slip but cost will not grow, show them this chart. The data says otherwise. The foundational schedule assessment questions are: is the project on schedule? Can I believe the schedule? Is it reasonable compared to similar missions? And is all scope represented? The question, can I believe the schedule, is separate from, is the project on schedule? A schedule can show on-time performance while being mechanically flawed or technically unrealistic. Credibility assessment requires external benchmarking. Comparing the current schedule to similar missions is the fastest way to identify optimistic assumptions. These questions should be asked at the beginning of every schedule assessment before looking at any health check metrics. The foundational schedule assessment questions are: is the project on schedule? Can I believe the schedule? Is it reasonable compared to similar missions? And is all scope represented? The question, can I believe the schedule, is separate from, is the project on schedule? A schedule can show on-time performance while being mechanically flawed or technically unrealistic. Credibility assessment requires external benchmarking. Comparing the current schedule to similar missions is the fastest way to identify optimistic assumptions. These questions should be asked at the beginning of every schedule assessment before looking at any health check metrics. Ratio-based questions: plan starts versus actual starts, plan completions versus actual completions, cost expended to complete tasks versus planned cost to complete. The example: plan was to spend $200,000 to complete 4 tasks, but only 3 were completed and $250,000 was spent, captures 3 problems at once: a schedule variance, a cost variance, and a productivity variance. These ratios are leading indicators because they measure task execution performance, which is the activity that drives all downstream metrics. BEI and CEI from the assessment tools section are formal versions of these same ratios. Understanding the concept here makes the formal metrics easier to apply. Critical path sub-questions: how realistic is it? How consistent is it from period to period? What is schedule reserve being used for? Is margin adequate? What do health check results show? A critical path that changes significantly from month to month is a symptom of either poor schedule maintenance or program instability. Both warrant investigation. Schedule reserve usage should be tracked specifically. What events triggered the use of margin, and have those events reduced future risk exposure or simply covered problems that have already occurred? These questions combine to build a picture of schedule health that goes well beyond what any single metric can provide. The 2 primary scheduling software tools, Microsoft Project and Primavera, along with numerous other tools available on the market. Primavera is the standard for large government programs because of its CPM capabilities, resource loading features, and compatibility with DCMA assessment tools. MS Project is widely used on smaller programs and in-house work. Tool proficiency is necessary, but as this module has emphasized, it is not sufficient. Knowing which button to push in Primavera does not make you a schedule assessor. If you do not have access to the scheduling tools your program uses, advocate for it. The analyst who cannot read the IMS directly is relying on someone else's interpretation. The Orion program calendar example: a long list of dates with milestones arranged chronologically. This is a calendar, not a schedule. A schedule has logic, dependencies, and resource loading. Many programs call their calendar a schedule and manage accordingly. The result is a program that tracks dates without understanding what is driving them. A calendar tells you when things are supposed to happen. A schedule tells you why they will happen when planned, which tasks must precede them, which resources are required, and which risks could affect the timing. If the document your program calls a schedule does not have logic links, resource loading, and float calculations, is a calendar. Manage it accordingly. A real IMS example. Impossible to see the entire schedule at once. Critical paths and major subsystems are filtered out from management briefing. The fact that the schedule cannot be shown in full on a single slide is not a problem. It is evidence that the schedule has the right level of detail to reflect actual work. Filtering from management briefings is the normal practice. You present the critical path and major subsystems, not the full IMS. The full IMS is the analytical tool. The filtered view is the communication product. When management asks for a one-page schedule view, they're asking for a filtered picture of the critical path. That is fine for communication. Never confuse it for the analytical product. Two primary methods for applying cost to schedule: cost loading and resource loading. Many people think they are the same. They are not. Cost loading assigns dollar amounts to schedule activities at an aggregate level. Resource loading assigns specific people, equipment, materials, and facilities to every task. Cost loading is faster and easier to maintain. Resource loading is more labor-intensive, but reveals overallocations and resource conflicts that cost loading cannot show. The choice between cost loading and resource loading depends on program size and analytical need. At minimum, cost loading should be applied at low WBS levels to enable meaningful EVM analysis. Resource loading details assign specific people, equipment, and facilities to every task. Very labor-intensive and cumbersome to maintain, but allows automatic cost and schedule integration. Resource loading is the best way to see what it actually takes to execute the work. It makes hidden resource conflicts visible that would not appear in any other format. The automatic cost and schedule integration that resource loading provides is what makes EVM most meaningful, because the cost is derived from the actual resource plan, not allocated from above. On large programs where EVM is contractually required, resource loading is usually the standard. On smaller programs, cost loading with careful WBS structuring is often sufficient. In a Mary Prince overbooking example, the resource allocation chart shows Mary Prince assigned to multiple tasks that overlap, making the schedule non-viable. This kind of overallocation is invisible in a cost-loaded schedule and invisible in a calendar. It only becomes visible in a resource-loaded schedule. Overallocated resources are one of the most common causes of schedule slip that were never actually achievable as planned. The plan was optimistic not because of incorrect task durations, but because of impossible resource assignments. When assessing a schedule for the first time, checking resource allocation is one of the highest value activities. Overallocations reveal a schedule that cannot be executed as written. Schedule health checks are valuable tools that provide indication of schedule viability, but they do not guarantee a credible schedule if passed, and do not automatically condemn a schedule if failed. DCMA, STAT, and GAO all have their own health check frameworks that vary substantially from each other. The one your program is subject to depends on contract requirements and oversight relationships. The example on this slide shows a schedule that fails health checks, which is a clear signal that the schedule quality needs to improve before performance measurement against it is meaningful. A health check failure is the beginning of the analysis, not the end. The next step is identifying which specific metrics failed and what the structural problems are. Health checks cannot tell you whether the logic is correct or whether durations are adequate. The spell check analogy: grammar can still be wrong even when spelling is correct. A schedule can pass every DCMA metric and still have completely wrong logic, tasks in the wrong sequence, durations that ignore historical cycle times, or dependencies based on assumptions rather than technical reality. The spell check analogy is one of the most useful mental models in this course. It properly calibrates what health checks can and cannot tell you. Health check results are the starting point for schedule quality assessment, not the ending point. Always follow a passing health check with a ground truth review of the critical path. The 14-point assessment table: logic, leads, lags, relationship types, hard constraints, high float, negative float, high duration, invalid dates, resources, missed tasks, critical path test, CPLI, and BEI. These 14 metrics are fast becoming the standard across multiple industries. They assess the structural integrity of the CPM schedule, not realism, but logical completeness. The thresholds matter. 0 negative float, 0 leads, 0 invalid dates are hard stops. High float below 5% and high duration below 5% are manageable thresholds. The BI at the bottom of this table, ratio of completed tasks to tasks planned, goal greater than or equal to 1.00, is the execution performance metric in the DCMA framework, covered in detail in the next few slides. GAO's 10 best practices: capturing, sequencing, resourcing, and establishing durations for all activities, traceability, valid critical path, reasonable float, schedule risk analysis, updating with actual progress, and maintaining a baseline. The GAO framework is more principle-based and less metric-driven than DCMA. It is used by GAO auditors to assess whether a program schedule is reliable as a forecasting tool. The GAO guide is intended to help managers and auditors ensure that program schedules are reliable. The reliability of the schedule determines the credibility of forecasted dates for decision-making. If your program is likely to face GAO scrutiny, familiarize yourself with this framework. The principles here are the lens through which the auditors will evaluate your schedule. Dependencies. Each activity must have a predecessor and successor, with exceptions only for start/finish milestones and summary tasks. Tasks without logic cannot drive or be driven. An unlinked task is a floating island in the schedule. It will never drive the end date and will never be driven by anything else, making it analytically invisible and potentially masking a real critical path risk. Checking dependency completeness is one of the first things a schedule assessor should do. Open ends and missing links are the most common structural problems. A schedule where every task is connected through a complete logical network is the foundation for meaningful critical path analysis. Without complete logic, the critical path is fictional. Redundant logic. Schedulers sometimes add extra dependency links to prevent a schedule from slipping when a health check would otherwise fail. This is a workaround, not a fix. Redundant logic is often inserted under deadline pressure to get a schedule to pass a health check review before a major program review. It makes the metrics look better while hiding real schedule risks. Redundant logic makes it difficult to trace schedule logic, which obscures the true critical path and makes recovery analysis less reliable. When you find redundant logic, it is a signal to ask what the scheduler was trying to hide from the health check metrics. The answer usually reveals a structural schedule problem. Two main constraint types: hard constraints like must finish on and start no later than, which override schedule logic, and soft constraints like start no earlier than, which constrain in one direction only. Hard constraints are dangerous because they can force a schedule to show on-time performance, even when a logic would indicate a delay. The constraint overrides the calculation. Soft constraints are less problematic but still impact critical path calculations and should be reviewed to verify they are grounded in real program requirements rather than scheduling convenience. Excessive hard constraints in a schedule are a warning sign. They suggest the scheduler is managing the appearance of the schedule rather than the integrity of it. High duration. DCMA defines it as over 2 months. GAO defines it as over 44 working days. Long tasks should be broken into multiple tasks to enable higher fidelity tracking. A 200-day task that is 50% complete in the schedule tells you almost nothing about whether it is actually on track. A 20-day task that is 50% complete is much easier to assess. There is nothing magic about 44 days. It is a threshold that balances scheduling granularity against maintenance burden. The principle is that shorter tasks enable more meaningful progress reporting. When you see a schedule where most critical path tasks are over 2 months, you're looking at a schedule that will not give you early warning of slip. The task durations are too coarse. High float. Activities with total float over 44 days may indicate inaccurate logic or a missing task. The 282-day float example shows a widget that is not needed until a year after its scheduled completion. High float on a task that should be on or near the critical path is usually a symptom of missing logic, a dependency that should exist but was not captured. The 282-day float example is not rare. Schedules frequently contain tasks that look like they have enormous schedule cushion because the downstream dependencies are not properly coded. When you find a task with suspiciously high float, trace its successors. The most common finding is that one or more critical dependencies are missing. BEI formula. Tasks actually completed divided by tasks planned to be completed in the baseline period. In the example, 4 tasks completed out of 5 planned give a BEI of 0.80. BEI can go over 1.0 if more tasks are completed than were planned, which can happen when teams front-load easier work or when tasks planned for later periods are completed early. A BEI of 0.80 means 80% of the planned task completions were achieved. On its own, this suggests the program is behind, but the nature of the uncompleted tasks matters. Uncompleted critical path tasks are more serious than uncompleted float tasks. BEI gives you an execution performance ratio that is comparable across programs and over time. It is a clean, objective measure that does not require EVM infrastructure to compute. HMI formula. Tasks actually completed on or before their baseline date divided by tasks planned to be completed. HMI cannot exceed 1.0. In the example, 3 tasks completed on time out of 5 planned give an HMI of 0.60. The distinction between BEI and HMI is timing. BEI counts any completion in the period. HMI counts only completions that hit their baseline date. An HMI lower than BEI indicates that some tasks that were completed late relative to their baseline. The gap between BEI and HMI measures how much of the completion is slipping. HMI is the stricter of the two metrics. It is the one that tells you whether the schedule is being executed as planned versus being executed better or worse than planned. CEI formula. Tasks from status period A that were actually completed by status period B, divided by tasks planned in period CEI cannot exceed 1.0. In the example, 3 of 5 give a CEI of 0.60. CEI measures carryover. How many tasks that should have been done last month are still outstanding this month? A consistently low CEI means the schedule is accumulating unfinished work. Used together, BEI, HMI, and CEI provide a three-dimensional picture of schedule execution health. Are tasks being completed? Are they being completed on time? And are carryover tasks being cleared? If CEI is consistently below 0.8 for 3 or more months, the program has a carryover problem that will eventually compress the remaining schedule. This is an early warning signal for critical path slip. Critical path analysis is the determination of the sequence of activities that defines the minimum time to complete the project and whose delay will directly delay the project end date. Critical path analysis is one of the most frequently misapplied concepts in project management. The next few slides address the most common misconceptions. Understanding the critical path is not optional for schedule assessment. It is the foundation. Without knowing the critical path, you cannot assess which schedule variances matter and which do not. Before you can answer whether a schedule slip is a problem, you have to know whether the slipping task is on the critical path. Using the longest path method, the critical path is the sequence of activities with the earliest finish equal to the latest calculated early finish for the project, tracing back to the project start. Potential critical paths are paths with very little float that could become critical if delayed. These near-critical paths deserve almost as much attention as the critical path itself. The diagram shows multiple paths through the schedule and highlights one as the critical path. The longest path through the network is the one that defines the end date. A project with only one critical path and many near-critical paths is at higher risk than a project where the critical path is clearly dominant and other paths have substantial float. Common mistake: confusing critical activities with critical path. Sweeping the floor can be a critical path activity if it must be completed before the next activity can proceed. Customer approval is obviously more important than cleaning the fabrication area. But if cleaning is a required prerequisite for the next task, it is on the critical path as defined by the schedule logic. This distinction matters for resource allocation. The critical path task that should get additional resources is the cleaning task, not the customer approval task, if cleaning is what is driving the end date. Critical path analysis is structural, not organizational. The analyst who confuses importance with criticality will allocate resources to the wrong tasks. For methods for determining critical path: longest path, lowest total float, negative total float, and longest path value method. Longest path is the original concept and is recommended for programs with multiple calendars and activity constraints. Lowest total float is the most widely used in practice. Negative total float: any activity with float less than 0 is on the critical path by definition, even if other activities have lower negative float values. Knowing all four methods matters because different scheduling tools use different approaches by default. An analyst reviewing a schedule needs to know which method was used to correctly interpret the critical path output. 9 critical path assessment questions. Does content pass the common sense test? Does task sequence make sense? Is there enough detail to identify interface points? Are there multiple near-critical paths? Are durations realistic? The common sense test is underrated as an assessment tool. If the critical path runs through tasks that experienced engineers would not consider logically dependent, the schedule logic needs review. Multiple critical and near-critical paths increase program risk because a slip on any one of them threatens the end date. Programs with only one critical path have more flexibility. These 9 questions are the interview protocol for schedule assessment. Apply them systematically before forming any conclusion about schedule health. First step: identify variances by comparing baseline versus current dates. Identify tasks where slippage exceeds established thresholds and ask why slippage occurred and what the impacts are. The baseline IMS is the contractual reference. The current IMS is the working document. The variance between them is the history of what the program promised versus what it delivered. Threshold setting for schedule variance reporting should be done at the beginning of the program, not after variances have already appeared. Identifying the variance is the easy part. The value is in the analysis of cause and impact that follows. The variance number is the beginning of the conversation, not the end. Second step: perform analysis. Is the variance on the critical path? What caused it? Can work be parallelized to recover? Are resources adequate? Are additional shifts needed? The question about whether additional shifts are cost-effective to address a variance off the critical path is important. Adding shifts to a non-critical task wastes money and does not help the end date. Fix the problem before additional time is lost. This is advice about urgency. Every day of investigation without corrective action is a day of additional slip. The analysis produces a specific answer to the program manager. Here is the cause. Here is the impact. Here is what needs to happen to recover. Here is the cost of recovery. 2 common recovery methods. Fast-tracking works activities in parallel rather than in series, and crashing adds labor to critical path tasks to compress durations. Fast-tracking increases technical risk. Tasks that were designed to be sequential are being parallelized. It can work, but often introduces rework when downstream tasks begin before upstream tasks are complete. Crashing increases cost. Throwing labor at critical tasks is expensive and often less efficient than planned staffing. Productivity loss from additional shifts applies here. Recovery plans must include both the schedule impact and the cost impact of the recovery method. A plan that recovers the schedule by crashing without costing the cost impact is incomplete. Schedule basics for the integrator. Scheduling is a specialized skill. Many people think they're schedulers because they use MS Project. Schedule analysis requires different skills than scheduling itself. Running a health check tool does not make you a schedule analyst any more than owning a stethoscope makes you a physician. The tool is a starting point, not the assessment. Cost and schedule are closely related. The integrator who understands scheduling brings a capability that most program teams are missing: the ability to connect a schedule variance to a cost forecast. The integrator does not need to build schedules. They need to be able to read, challenge, and interpret them, which requires a different but equally important skill set. Looking at program schedules critically, does the workflow seem logical? Are durations in hours or days? Are the same durations used over and over? Are they all round numbers? What is the basis for the durations? Uniform round number durations are a classic indicator of a schedule built by someone who did not understand the work. Every task set to 1 week, every task set to 30 days. The basis for durations is the most revealing question. If the answer is that we use the same durations as in the last program, that is not a basis, that is a copy. I'll look for changes over time in the schedule. A task that was 30 days in last month's IMS and is now 45 days represents a change in scope or execution that the analyst needs to understand. Track the key indicators: schedule margin loss, critical path slippage, milestone slippage, integrated cost and schedule, and rules of thumb. Schedule margin loss is one of the most sensitive early warning metrics. If schedule reserves are being consumed faster than risks are being retired, the program is in trouble before any critical path slip appears. Rules of thumb for schedule: the spacecraft rule, the CDR to launch delay distribution, the cost and schedule growth correlation are the reference benchmarks for all of these tracking activities. The integrator's schedule tracking dashboard should show these 5 indicators every month. Negative trends in any one of them are signals to look more deeply at the schedule. Transition to the empirical evidence section. What does the historical record of NASA and DoD program schedules actually show about delay patterns and their cost consequences? The studies in the next few slides are not anecdotes. They are systematic analyses of 40 to 114 real programs. They provide the benchmarks against which any current program schedule should be compared. How do you use the information? By calibrating current program schedule health against what similar programs look like at the same phase of development. The historical data makes schedule assessment defensible. When you tell a program manager their schedule is aggressive, the historical benchmarks tell them how aggressive. The actual versus planned schedule chart, showing that most schedule increases occur in the costly post-CDR phase, not in the early formulation phases. The fact that most growth occurs post-CDR is significant for where PP&C places its analytical emphasis. CDR is the last gate before the expensive fabrication and test phases. Programs that enter Phase D with schedule margin intact are far better positioned than those that consume all their float by CDR. CDR float is the most valuable schedule insurance a program can carry. The analyst's job before CDR is to protect schedule margin. The analyst's job after CDR is to identify INT and integration problems before they lead to launch delays. Histogram of launch delays from 114 NASA missions. Range of -5 to 159 months. Mean of 25.8 months. Median of 16 months. standard deviation of 30.55 months. The median delay of 16 months is the most practically useful number. Half of all 114 missions slipped by more than 16 months. This is not a tail risk, it is a central tendency. The mean of 25.8 months being higher than the median of 16 months indicates a small number of very long delays pulling the mean up, but even a median performance is a significant slip. When a program plan shows zero schedule contingency and a committed launch date, show them this histogram. Ask them which decile of this distribution they expect to fall in. Delay distribution by mission theme and project phase across astrophysics, earth science, heliophysics, and planetary. Most missions delay post-CDR regardless of theme. Planetary missions delay least often, primarily because they have fixed launch windows that force schedule discipline, and the consequences of missing a window are so severe that everyone takes the schedule seriously. The CDR to launch phase accounts for the largest percentage of delays across all four mission categories. INT problems are the dominant cause. This chart is the empirical answer to the question of where PP&C should focus schedule risk attention. The data says post-CDR INT, regardless of mission type. One of the most important lessons in program management is that schedule and cost cannot be evaluated separately. For most government and NASA programs, labor is the largest cost driver, which means schedule delays almost always result in cost growth. Simply put, schedule equals dollars. As a result, a cost estimate is only as credible as the schedule that supports it. If the schedule is unrealistic, the cost estimate is unrealistic as well. Historical NASA data reinforces this relationship, showing that missions experience an average schedule growth of approximately 57% between initial planning and launch. Many of those delays occur during integration and test activities, where hardware and systems often behave differently when brought together than they did during individual testing. The key takeaway for analysts is that schedules should be evaluated against historical performance and realistic assumptions. When a program presents an aggressive schedule with little or no margin, history suggests additional scrutiny is warranted before accepting the plan as achievable. Supply chain is not formally a PP&C discipline, but is tightly linked to scheduling. Supply chain personnel work closely with PP&C analysts to manage need dates and ensure schedule commitments are maintained. Late deliveries from suppliers are one of the most common drivers of post-CDR schedule slip. The subsystem A Late Delivery in the DoD case study is a direct illustration of this. The coordination between PP&C and supply chain is informal in most organizations. Establishing regular communication with procurement and logistics is a best practice, not a standard. If you're doing schedule assessment without visibility into the supply chain, you have a blind spot in the most common failure mode for post-CDR programs. Supply chain defined: the flow of goods, services, and information from suppliers to customers. For parties involved: suppliers, manufacturing, distribution, and customers. From a PP&C perspective, the supplier is the most critical player. They hold the hardware that will either support or threaten the integration and test schedule. Supply chain risk manifests in PP&C data as schedule variance, late deliveries, cost variance, expediting fees, rework, and workforce variance, INT teams waiting for hardware. The PP&C analyst who tracks supplier delivery status against the IMS will see schedule problems 6 to 12 weeks before they appear in the critical path metrics. Key supply chain functions: procurement, logistics, inventory management, production planning, quality assurance, and customer fulfillment. Production planning and quality assurance are the two supply chain functions most directly connected to PP&C schedule analysis. Production planning determines when parts will be available. Quality assurance determines whether they will be accepted. A part that fails quality inspection after scheduled delivery is functionally equivalent to a late delivery from a schedule impact perspective. Build a relationship with the quality assurance team on your major subcontracts. First article test results and acceptance test failure rates are early indicators of delivery risk. 3 questions testing Module 2 concepts, schedule health check limitations, BI interpretation, and applying the 114 mission historical data to current program management practice. Q1 requires the spell check analogy. A schedule can pass all 14 DCMA metrics and still have wrong durations and incorrect logic. Q2 requires explaining BEI as a task execution ratio and identifying root causes. Q3 is the most integrative. It requires applying the finding that most delays occur post-CDR due to INT problems and translating that into specific PPNC monitoring priorities for a program between CDR and launch. These 3 questions measure whether students understand the limitations of mechanical schedule health, can interpret execution metrics, and can apply historical benchmarks to real decisions. Up next, we'll explore earned value management, one of the most widely used tools for measuring and assessing program performance. In this module, you'll learn how planned value, earned value, and actual cost work together to provide insight into cost and schedule performance, forecast future outcomes, and identify emerging risks before they become major issues. We'll examine key metrics such as CPI, SPI, EAC, and TCPI, and learn how to interpret performance trends that often signal future overruns. By the end of the module, you'll understand how EVM supports informed decision-making and helps program teams maintain effective control of cost, schedule, and overall program performance.